Now that we understand the sinusoid and the makeup of a sinusoidal wave, let's take a look at the angular measurement of a sine wave. We're going to look at something in terms of what's called a phasor, which is a vector relationship, and how we decompose that sine wave representation and turn it into something that has a magnitude and an angle. So as you've seen, sine waves can be measured along the horizontal axis on a time basis. However, since the time for completion of one full cycle or any portion of a cycle is frequency dependent, it's often useful to specify points on the sine wave in terms of an angular measurement expressed in degrees and radians. So what we're going to do in this section here is we're going to look at the sine wave representation in terms of angles. We're going to define what the radian is, converting radians to degrees, and determining the phase angle of a sine wave. A sinusoidal voltage can be produced by an alternator, which is an AC generator. There is a direct relationship between the rotation of the rotor in an alternator and the sine wave output. Thus, the angular measurement of the rotor's position is directly related to the angle assigned to the sine wave. So what we need to look at is something called the unit circle and breaking down the radian relationship. In angular measurement, a degree is an angular measurement corresponding to 1/360th of a circle or a complete revolution. A radian, which is a measure of an angle, is an angular measurement along the circumference of a circle, or a segment, if you will, if we only go part way around the circumference, along the circumference of a circle that is equal to the radius of a circle. 1 radian then is defined as 57.3 degrees as shown in the diagram. In a 360 revolution, there are 2 pi radians. So we go from 0 to pi all the way back around to 2 pi. We use the Greek letter pi to represent the ratio of the circumference of any circle to its diameter and has a constant value of approximately 3.1416. Scientific calculators have a pi function on them. Again, if you take a look at your calculator or the Casio calculator, there is a key on here. In this case, you have to do a shift. You have to do a shift, and then on the bottom here where it says times 10 to the x, you press that and you get your pi function. Always use the pi key on your calculator. Don't use, unless you're told specifically in the problem, I only need it good to 3 places, or 2 decimal places, 3.14. Always use the pi key on your calculator when you're making calculations. So the table to the right here lists several values of degrees and corresponding radian values. These angular measurements are illustrated in 1117. Okay, so you can see how in 1117 we take the circle and cut it up into pieces here from 0 to pi over 2, cut that in half, pi over 4. From pi over 2 to pi, cut that in half. We have 3 pi over 4 or 3/4. Go to 3 pi over 2 and cut that in half. We have 5 pi over 4. And then back to pi, we have half of that, 7 pi over 4. So these are common radian measures around the unit circle in this case. You can see from the diagram here on the right, the degrees to radians relationships for common for common angles and degrees, and to radians we're going to see that we can do interval relationships, those that are not necessarily common. So how do we do that? Well, we do something by creating what's called a radian to degree conversion. Degrees can be converted to radians, knowing that a radian has a conversion of pi radians by 180 degrees and multiply times degrees. So in this case, if I had 30 degrees and I divided it by 180 degrees, the degrees cancels out, and I'm just left with then 30 divided by 180 times pi radians. To go the other way, degrees is equal to 180 degrees by 2 pi. We've just inverted the relationship times radians and pi. So if it was pi radians, and we were converting to degrees, you can see pi radians divided by pi radians cancels out, and we're left with 180 degrees. So in some examples here, convert 60 degrees to radians, convert pi over 6 radians to degrees. So if we run this through the relationship where we have pi radians over 180 divided by 60, we get pi over 3, or 1/3 pi radians. Converting then from radians to degrees, 180 degrees divided by pi radians, multiply that times 1/6 pi radians, the pi's cancel out, 6 into 80 goes 30 times, so we have 30 degrees. So it's fairly simple. You'll get used to it very quickly. Again, write this relationship down in your folder and your notebook and keep it handy. So in looking at how do we define these on the sine wave? Well, sine wave angles are based on 360 or 2 pi radians for a complete cycle. If we go from 0 to 0 to 360, or 0 to 180 to 360, or 0 to pi to 2 pi, we've basically gone in a circle. So if you think back on that circle representation, a half a cycle is 180 or pi radians, a quarter cycle is 90 or pi over 2, and so on. So what we have here then is a relationship that really is a circle that's been unwound. So we take the circle, we spin it around, we unwind it, go from 0 to 2 pi or 0 to 360. We've got the same relationship here. I like to think of this like putting an ink pen, on a wheel and then running it along a piece of paper. While that wheel is spinning, the pen is going, the pen is basically going up and down, but as you're moving it, it's drawing a sine wave. So what are the phases then of a sine wave? The phase of a sine wave is an angular measurement that specifies the position of that sine wave relative to a reference. So as we can see, one cycle of a sine wave is used as the reference. So one time around. If it does it again, it's just repeating the same thing over and over again. So we only need one cycle. Note that the first positive going crossing of the horizontal axis, the 0 crossing right here in the middle, is at 0, and the positive is at 90. So we're at 0, 90, 0, minus 90, or 270, back to 0. So we can look at this as 0, pi over 2, pi, 3 pi over 2, 2 pi. So the cycle is completed at 2 pi when the sine wave is shifted right or left with respect to the reference. Then we have a phase shift requirement, which we will get into later. So in our illustrations here, you can see we have placed 2 sine waves on the same axis here. One of them is shifted by 90 degrees positive. The other one here is shifted by 90 degrees negative. Okay, this comes into play when we start dealing with things called inductors and capacitors. In part A, the sine wave B is shifted to the right by 90 or pi over 2 with respect to the fixed A sine wave. In terms of time, the positive peak of sine wave B occurs later than the positive peak of sine wave A because time increases to the right along the horizontal axis. So in this case, sine wave B is said to lag sine wave A by 90 degrees or pi over 2 radians. Stated another way, sine wave A leads sine wave B by 90 degrees. Okay, just try to get this down as a concept. Again, you're going to use it later when you get into AC circuits, your 132 class. So if we look at the example here, what are the phase angles between the 2 sine waves, parts A and part B? So if we look at part A, we've got 2 sine waves. They both have different amplitudes, but you can see that B is shifted so that its starting point is 45 degrees off from A. If we look at B over here, we've got A crossing at the 0, but B is 30 degrees negative off from A. So in figure A, the 0 crossing for sine wave A is at 0, and the corresponding zero crossing of sine wave B is at 45. There's a 45-degree phase angle between the two waveforms, with waveform B lagging A. In B, the crossing is at minus 30 for B, and the corresponding zero crossing at A, again, is at 0. So there's a 30-degree phase angle between the two waveforms, with sine wave B leading sine wave A. So we can get a picture sinusoidally of what's going on between these two signals. Later, we're going to look at them in terms of a phasor. So as a practical matter, when you measure the phase shift between two waveforms on an oscilloscope, you should make them appear to have the same amplitude. This is done by taking one of the oscilloscope channels out of the vertical calibration and adjusting the corresponding waveform until its apparent amplitude equals that of the waveform. Okay, and you'll see this. If you have a problem with that, ask your lab instructor. Polyphase power, multiphase, three-phase, however you want to think about it. Typically, your power down the distribution line into your home for residential power is three-phase power. How it's broken up into your neighborhood is based upon each one of these three phases being delivered to a home. Sine wave formulation. A sine wave can be graphically represented by a voltage or a current on the vertical axis and by angular measurement, whether it's degrees or radians, along horizontal axis. This graph can be expressed mathematically, as you will see. So in this case, we have a sine wave formula. And what we do is we take a look at the sine wave. It is characteristically modeled as y times the amplitude times the sine of theta. That's why we call it a sine wave. So if we look at it further, we can see that the voltage, this is a time relationship, is the peak voltage times the sine of theta. Well, if the peak voltage is 10 volts and the angle is 60 degrees, sine of 30, so if I take the sine of 30, I get 0.886 times 10 gives me a voltage of 8.66 volts. Okay, so we can see that on the sine wave here itself, right here at 60 degrees, and we see that it's 8.66 down from the maximum. So in looking at phase shifted sine waves, as we said before, we give it some angle. In the mathematical relationship for the sine wave formula, we have to show the shift as the difference in the angle. So in this case, theta minus phi, or theta plus phi, depending on whether it's lagging or leading. If we look at the example here, we've got three sine waves here, three signals, A, B, and C, and we're going to map which each one is according to its maximum peak value and its angle. So for the first one, A, we're starting at the origin, so Vp sine theta, 10 volts times the sine of 90 gives us 10 volts, our full 10 volts. For B, we're at Vp sine of theta plus phi of B. So in this case, we have 5 volts, a sine of 90 plus 20 degrees for B gives us then 4.7. For sine wave C, we are 90 minus 45 degrees with a maximum of 8 volts. So we have 8 volts times the sine of 45 degrees, because 90 minus 45 gives us 45. 0.707 is the sine of 45 degrees. We get 5.66 volts. Okay, so that's how we deal with the sine wave formula and phase shifted signals.